Okay, section 5.5 is all about approximations. There's two different types of approximations we're going to cover. Today we're going to cover something called linearization. Linearization is used to approximate the value of a function. Tomorrow, or whenever we have class next, we're going to talk about differentials, which is used to approximate change. So, first off, what is linearization? Linearization is the process of approximating a small section of a complex curve with a linear equation. Thus the name. A linear equation is just an equation of a line. So basically it takes a complex curve and says, hey, that's kind of pretty complex, a lot of curves to it. Can we approximate a small portion of that with just a line? So here's an example. I've got the equation x cubed minus 10x plus 16, and it has a linear approximation of y equals 2x for any values near x equals 2. We're going to graph these and take a look at what it means to be a linearization of a problem or a linear approximation. Okay, so here's our original x cubed equation, and here's our linear approximation. Now, I want an equation that approximates values of this original. So you can tell most of the time this blue line is a really horrible approximation of this red line. However, right here, near value of x equals 2, those are actually pretty close to the values of the red line. So this blue line is a good approximation of that red curve, but only over these values right here. I can zoom into that point more and more. And as I zoom in, I can see that just that section, I've got a pretty good approximation. In fact, let's zoom in just a little bit more to see what happens. All right, so you can see the closer I zoom in, the closer I am to being a very, very, very good approximation. In fact, right around here, there's almost no difference between the blue line and the red line. Of course, that's also super zoomed in. So linear approximations are good approximations of the original function, but only over small distances, small values of x. Okay, so if linear approximations are only good approximations over small values, why would we use them? So what's the point of linearization? Well, the point is when a small amount of error is allowable and you're covering just a small number of values, linearization takes a complicated equation and makes it relatively simple. Here I've got an original equation of x cubed minus 10x plus 16. There's my approximation of y equals 2x. Now I already have these values filled in, so I've got an exact value. But if those weren't filled in, which equation would you rather use to approximate these values of x? All right? They're super quick with y equals 2x. Just plug them in. 2 times 2 is 4. 2.01 times 2, well, that's easy, 4.02. 2.03 times 2, 4.06. 4.1. Those are really quick and easy. And yes, they're not going to be perfect, but it's a pretty darn close approximation. And in fact, at 2, it's exactly perfect. And just a little bit off there, tiny bit off there, not very far off. So I have got very good approximations over these small values here. So why do we use linear approximations? Well, they can be a good quick approximation of a value over a small distance. Not a ton of applications, but it does kind of give a good indication of calculus. It kind of teaches what linear approximation is. So there's a lot of good benefit for a deeper understanding of functions in general with these types of problems. All right, so last question. If it's something I need to do, how do we do it? It's actually pretty easy. You've been doing it for a while. The linearization of a function near a given point is simply the equation of the tangent line at that point. Because at that point, I want to be exactly right on, and I just want my function to be as close to the original curve for as long as possible, which would be a tangent line. It touches it once, and it stays pretty close. It has the same slope. So a linearization near a given point is just the same thing as finding a tangent line, which we've done for a while. So, an example. If you are asked to find the linearization of this equation for values near x equals 0, that's just the same thing as finding the tangent line for values near x equals 0. So, how do you find the equation of a tangent line? You need two things. You need a point, and you need a slope. The point is going to be 0, comma something. How do you find the something? Well, you plug the 0 back into the original. If I plug a 0 into there, I'll have the square root of 0 plus 1, which is the square root of 1, which is just 1. So the point is 0, comma 1. How do I find slope? Well, in calculus, you find slope by using the derivative. My original equation was, I'm going to rewrite it as x plus 1 to the 1/2. So my derivative is going to be 1/2 x plus 1 to the negative 1/2, which many of you guys prefer writing like this. 1 over 2 x plus 1 to the 1/2, or let's even write that as square root of x plus 1. Particularly, I care about the slope when x is 0, so let's find y prime of 0. That'll be 1 over 2 times the square root of 0 plus 1, which is just 1/2. All right, I've got a point of 0, comma 1. I've got a slope of 1/2. So I can write my linearization. Y minus 1 equals my slope times x minus 0. You can definitely leave it like that. This one's actually pretty easy to put into slope-intercept form if you like that one better. 1/2 x plus 1. There is my linearization, also known as a tangent line. Part B is asking, how accurate is the approximation of L of 0.1 compared to F of 0.1? So capital L stands for your linearization, little f stands for the original function. So it's just asking like, hey, how accurate is your approximation when you put in a 0.1? So to find out, find the two of those. This one, let's go ahead and call that L of x because it asked me to. So let's call that L of x equals 1/2 x plus 1. So for this question, part B, my linearization at 0.1 would just be 1/2 times 0.1 plus 1, which is 1.05. My original function would be the square root of 0.1 plus 1, which is the square root of 1.1. I don't know that in my head, so I'm going to have to use the calculator for that. That's 1.048 repeating. So as far as how accurate I am, I'm pretty darn accurate. It looks like I'm within 1/100th, right? Here's 0.05, that's 0.048. I'm definitely within 1/100th. So I am accurate within 0.01 units. All right, that's linearization. It's finding a tangent line. Your assignment is 1 through 7, just practicing linearization, and 41. Again, as always, if you need help, see me during my office hour. I'm more than happy to help you. See you later.